2004B that you wanted. All right, so when you look at these free response questions, the very first thing you have to do is look at the species that you're working with. So I know that I'm working with silver and zinc, and you have to use that standard reduction potentials chart in order to kind of figure out who's going to be reduced and oxidized. If you can figure out who's reduced and oxidized, then you can be able to answer the questions a little bit easier. So I'm going to look here for silver and zinc on my reduction potential chart. And when I found those, I found that zinc is this. So Zn2 plus 2 electrons yields zinc. And it has a standard reduction potential of negative 0.76 volts. Then I do the same thing for silver, Ag, I'm looking for them. Ag is on this side. Ag plus 1 electron goes to Ag. That value is 0.8 volts, okay? Now, whenever I look up my standard reduction potentials, what this tells me is which one of these species is going to be reduced. So I know that the more positive value out of these two should be the species reduced. So if I look at these two, 0.8 is more positive than negative 0.76. So that means that the silver is the species that's reduced, which must mean that this is the species that is oxidized. Now that I know who's reduced and who's oxidized, I then can write my balanced equation. So how I know where to start? I know that zinc nitrate has to be in the reaction, zinc needs to be in the reaction, silver needs to be in the reaction, and silver nitrate needs to be in the reaction. Well, which one I write on which side depends on who's reduced and who's oxidized. These species that are in the solution with the spectator ions, those are your ions. So this AgNO3 is this Ag+. This ZnNO3 is the Zn2+. So if I want my Ag to be reduced, I want my charge to go down as from my reactants to my products. So I'm going to write where the solution, AgNO3, is going to be my first reactant. So I'm going to have AgNO3 plus, and that's going to yield Ag solid, okay? Now, because zinc is oxidized, I want to start as the solid because that's a zero oxidation state and go up in charge. So I'm going to go to the solution, which is where my charge comes from, as my product. So it's going to look like this. Zn yields ZnNO3 2. Now that I have my foundation, I then can balance my reactions. So there's going to have to be a 2 in front of both of the Ags in order to balance that. Now what we do is we assign solubility rules. Silver nitrate is aqueous. Zinc is a solid. Notice how this doesn't get a charge. It's because it's my metal zinc. Solids that do not are not paired with anything, that are not classified as aqueous, do not get a charge. Same idea here for silver, and this is a solution that is aqueous. All right, now I have a spectator ion, which is nitrate. So now what I do is I bring everything down. Now what's very important to remember is that if it's aqueous, I have to bring it down as an ion because that's how it is in the solution. So 2Ag plus aqueous, an ion because it's aqueous, plus ZnS. This does not get a charge, it's just 0 because it's my solid. Yields 2Ag plus, that is a solid, that does not get a charge because it's a solid, plus Zn2 plus aqueous. This does get a charge because it's aqueous. All right, so this would be my balanced net ionic equation. Now notice how I said that the Ag has to be reduced. You see how it's going from positive to 0. It is being reduced. I said that because this is reduced, this has to be oxidized. My zinc is going from a 0 to a 2+, so it is being oxidized. So this is how you figure out how to write your net ionic equations for a lot of these galvanic cells. You first have to look at this and then figure out what's happening from there. Now for the next part, we want to calculate the standard E cell for the reaction. So remember, standard E cell is equal to reduced minus oxidized value. So I take my reduced value, which is 0.8, minus oxidized, which is negative 0.76, and that gives me my answer of 1.56 volts. So that is my answer for part B. Now, for the next one, it wants us to label the anode and the cathode on the dotted lines provided. So I have to figure out if my zinc or my silver is the anode or the cathode. And how I know that is my cathode is always reduced. Think of red cat. My cathode is always reduced. So since Ag is reduced, Ag here is going to be my cathode. That must mean that zinc here is my anode. And I don't think that this question asks it, but if it asks which way do my electrons travel through my wire, remember that it always goes anode to cathode, okay? Now, the next part says indicate in the boxes below the half cells the concentration of AgNO3 and the concentration of ZnNO3 that are needed to generate an E cell. Your biggest keyword here is the fact that it is standard. And how I know it's standard is this little not symbol right there. That tells me that both this solution and this solution are 1 molar each. So they are both 1 molar because of that little symbol, which means standard conditions. Now, the next question says, how will the cell be affected if Ki is added to the silver half cell, and then justify my answer? So I'm going to refer to this balanced net ionic equation for this, okay? Now when I add my, I'll just leave that up there. When I add my Ki to the silver, I have to think of solubility rules, okay? So I'm adding my Ki to this. Now here's what's happening. Potassium and nitrate will get together. It's basically a double displacement reaction. And silver and iodine will also get together. Because both of these get together, they form a precipitate, which is a solid that is in that solution. So if I have a precipitate that's made in this solution, what is it actually doing to the concentration of my Ag+? Well, think about it. My Ag+ is being used up to make a solid. So that means that my Ag+ is going to decrease in concentration because that precipitate is being formed. These guys are going away to make something else. So this is decreasing. And now that it's decreasing in concentration, I can either apply Le Chatelier's principle or my Q principle in order to answer the question. So if I was applying to Le Chatelier, this is my stress. This stress will cause my reaction to favor my reactants. And if I am favoring my reactants, then that is going to cause my E cell to decrease. Now remember how we justify these, refer to the practice problems, the key that I had. We want to say something along the lines of, according to Le Chatelier, if I add a stress to the reaction, by decreasing your Ag plus. And remember, the reason why we're decreasing that is because of precipitates being formed. Then that will cause my reaction to shift to favor my reactants, therefore decreasing my E cell value. Now, one other thing that I could do here is explain in terms of Q. Whenever you're explaining in terms of Q, you know that Q is equal to my concentration of my products raised to the coefficient divided by the concentration of my reactants raised to its coefficient. Now, for our coefficients and our products and our reactants, what we would plug in here, my products would be Zn, so that would stay 1. And Zn's concentration, or Zn's coefficient, is 1. For my reactants, however, I don't have a numerical value for it, but I know it's going to be some number less than 1. And so if this is some number less than 1, let's just plug in a potential number. Maybe we cut it in half, so now it's 0.5. And my coefficient that is in front of that is 2. I can theoretically go through and potentially calculate my Q, and then based upon my Q number, I can figure out if Q is less than or greater than 1, what happens to log of Q, and then how log of Q affects my E cell. Now this would probably more on the terms of a Le Chatelier question because they don't give you any numbers. If they gave you numbers, you would definitely want to plug it in and use the Q approach. So I hope this helps a little bit. Let me know if you have any more questions.